When drawing Lewis structures, you'll notice a series of recurring patterns coming back again and again. The same sort of building blocks, in terms of bonding patterns and the positions of electrons, will appear again and again in organic compounds. Part of the regularity in these is a regularity in what are called electron pair domains, or regions of space containing one or more electron pairs. For instance, in the Lewis structure of CH4 that we talked about last time, we can identify four EPDs, or electron pair domains, regions of space where electron pairs are localized. These appear in the four positions that I'm highlighting in green. Other molecules have different numbers of electron pair domains that are less than 4. For instance, in the compound shown here, this imine possesses 3 electron pair domains, one corresponding to the lone pair, one corresponding to the single bond, and one corresponding to the double bond. Even though there are multiple pairs in the domain that you see here, we still call it a single electron pair domain because it's a single region of space enclosing electron pairs. The usefulness of thinking about Lewis structures in terms of electron pair domains comes in the correspondence between the number of electron pair domains and the molecular geometry at the atom of interest. The pattern in this idea is shown for you on this slide. Linear molecules, which have a 180-degree bond angle about the atom of interest, consist of 2 electron pair domains, and the electron pair domains are represented for you stylistically here in black. Similarly, trigonal planar centers arise in molecules that possess 3 electron pair domains, such as the imine that we looked at on the last slide. Finally, tetrahedral compounds possess 4 electron pair domains at the atom of interest. These geometries arise from the fact that the electron pair domains, because they're negatively charged, want to be as far away from one another as possible. To do this, they spread out in the geometries that you see here. So the propine that we drew on the last slide, then, we would expect to have a linear geometry, like so. Similarly, the imine, we would expect to have a trigonal planar geometry, being sure to consider that lone pair as part of the electron pair domains and part of the geometry. And finally, a representative tetrahedral compound is methane, and as you can see from the drawing up here, the tetrahedral geometry, because it's three-dimensional, introduces a new convention for us. So when drawing Lewis structures that possess three-dimensional elements, we need to draw what are called wedges and dashes to represent bonds that are coming out at us and going away from us, respectively. So the bond that you see drawn on a wedge, with the smaller end of the wedge towards the atom that's farther away, is coming out towards us. This hydrogen is closer to us than the carbon atom at the center. Similarly, for the bond that is dashed, the carbon is closer to us than the hydrogen. Thus, we represent that bond as going away from us by drawing it in a dashed fashion. And here again, the atom that is at the point of the dash is the one that's closer to us by convention. As I alluded to in the last video, there are really a very limited number of octet configurations about an atom. You'll see these patterns come back again and again as you're drawing Lewis structures. I'll go through a few of them here. So we saw the example of 4 electron pair domains with no non-bonding electron pairs in the example of methane, CH4. No non-bonding electron pairs with 3 electron pair domains would simply involve 2 single bonds and 1 double bond. And finally, with 2 electron pair domains and no lone pairs, we would be looking at a propine type structure or an alene type structure with 2 double bonds associated with the atom. When the number of non-bonding electron pairs is 1, we can immediately draw a lone pair associated with the atom A. 4 electron pair domains corresponds to an ammonia type structure, NH3. 3 electron pair domains is analogous to the case above, replacing a bond with a lone pair, like the imine that we drew before. And finally, with 2 electron pair domains, it would be analogous to this triple bonded case, except we would replace the single bond with a lone pair. I'll let you finish filling out this table on your own, but there's one more important issue that we need to address related to drawing Lewis structures, and that's the issue of formal charge. So within a Lewis structure, an atom may or may not be neutral. Whether or not it's neutral depends on how many electrons it has around it. To determine formal charge, we take each bond attached to an atom and divide it in two, giving one electron to one of the atoms in the bond and the other electron to the other atom. We then count the number of electrons around the atom of interest and compare that to how many electrons we would expect it to have based on its position in the periodic table. So for instance, in methane, the carbon has 4 electrons around it following this procedure of splitting each bond in half and giving 1 electron of each bond to carbon. Because carbon is in group 4a, we would expect it to have 4 valence electrons, and therefore this carbon has a formal charge of 0. Compare this case to the case of, for instance, ammonia, where now we've replaced carbon with nitrogen. The nitrogen still has 4 hydrogens around it, and so formally the nitrogen has 4 electrons around it. But because nitrogen is in group 5 rather than group 4, a neutral nitrogen we would expect to have 5 rather than 4 valence electrons. This means that with this bonding pattern, with 4 single bonds and 4 electron pair domains around the nitrogen, we would expect this to be positively charged. As you practice assigning formal charge in Lewis structures, you'll begin to notice patterns emerging. Take note of these patterns, as places where there are a lack of electrons or an excess of electrons will be particularly reactive positions in molecules that you'll see as we move forward.